Hi everyone, this is Module 9, Part 2 of Sound and Sound Waves. Go ahead and get your book out and your notes out so that you can follow along as we go through this. We are starting out on page 329, so turn to that page in your book, and there's a table 9.1, the speed of sound in certain mediums. All right, in the last video we talked about sound and the speed of travel through liquids, gases, and solids. Do you remember if sound travels faster in liquids than in gases? Or which one it travels faster in? So it travels the slowest in slowest in gases, and then a little bit faster in liquids, and the fastest in solids. And then do you remember if it travels faster in warm medium or cold medium? I say medium because it could be warm air, it could be warm water, cold, solid, whatever. So sound travels faster in warmer temperatures. Do you remember why? So remember that all substances have atoms that are in motion. Everything is moving in our universe. When temperatures are warmer, these atoms are vibrating faster, and sound waves can travel faster through atoms that are already moving, and they're moving more, and they're bumping into each other more. So the sound energy is transferred when the atoms bump into each other. So if a wave was to try to travel through this, it would be really easy. They're so close to each other, they're going to bump into each other, and it can just speed along there, right? And if the energy wave is trying to go through a medium that is moving slower, or it's farther apart, it's a gas, it has to get this one moving and then bump into this one to transfer the energy, and then get that one to bump into that one, and so it moves a little bit slower. All right, supersonic speeds. If we measure the speed of sound in miles per hour, speed travels at 760 miles per hour in air, and that's Mach 1. Now remember, it's going to travel a little bit slower as you get higher up because the air molecules are colder, but it's about 760 miles per hour in air. Anything traveling faster, that's a supersonic speed. So we say it breaks the sound barrier, meaning the object traveled faster than the speed of sound. And if it's twice as fast as the speed of sound, that's Mach 2. If it's 3 times as fast the speed of sound, that's Mach 3. So in 1947, an American fighter pilot flew his plane 45,000 feet above the ground where the air was colder. So the sound traveled a little slower, right? He reached a speed of Mach 1.06, traveling faster than the speed of sound. A supersonic speed is any speed that is faster than the speed of sound in a particular medium. A sonic boom is the thunder-like sound or the cracking produced as an object travels above Mach 1 or faster than the speed of sound. So little shrimp underwater, they can make a shock wave underwater with the snap of a claw, and they can make a little sonic boom underwater. Some gunshots reach supersonic speeds and make that sonic boom. A bull whip that was made thousands of years ago, that's a whip for bulls. When it was swung the right way, the tip traveled faster than the speed of sound, making that sonic boom. And some think that the Diplodocus may have been able to crack its tail faster than the speed of sound. Okay, so when a warplane travels faster than the speed of sound, it is moving air particles with great intensity. It's creating sound waves, so this is my airplane, and in front of it and also behind it. The waves travel at the speed of sound. So these waves are traveling at the speed of sound. However, if the warplane is traveling faster than sound, causing the sound waves to compress, the sound waves, they can't get out of the way of each other, and they combine into one single wave at the front of the plane, creating a shock wave. And so what's basically happening is their amplitudes are adding together right here. And the greater the amplitude, the greater the energy, and the greater the sound or intensity of the sound. And so that shock wave moves all the way to the ground, creating the very loud boom that you guys hear in your ears. Do you guys remember what the amp was? Remember, I taught you that silly phrase, nice amplitude, like when you're going surfing and you like how tall the waves are. So the amplitude is measured right here. It's like the height of the wave from the rest position. So the rate the wave's energy flows is called the intensity. The greater the amplitude, the greater the intensity. Intensity depends on the amplitude, but also the distance. So if you're really close to the source of the sound, the intensity will be higher, right? And if you're farther away from the source of the sound intensity will be less. It'll be lower. What is sound intensity measured in? Do you guys remember reading that in your book? So it's measured in decibels. D with a capital B. Decibels. If I can spell, there's an E right there. Decibels. Okay? So 1 decibel is equal to the 10th of a bell. Okay, and 1 bell is a 10-fold increase in sound wave intensity. So we're talking about sound intensity here, not pitch or anything else. So if you have a 20 decibel sound, it's like 10 times 10, which is 100 times more energy per second than a 0 decibel. And 30 decibels has 1,000 times more energy than 0 decibels sound. An increase of 10 decibels results in a sound wave intensity increase of a factor of 10. The human ears have a range of 0 to 130 decibels. 0 to 130 decibels. That's the human ear. And that's, I can't even say that number. I'll show you it. This many times its threshold before damage. So God really protected our ears with allowing us to hear this much sound intensity before it damages our ears. So when you turn up the volume on your TV or radio, you're causing it to produce sound waves with larger amplitude. Okay, larger sound intensity, larger amplitude of the wave. So look at page, I'm not sure, 331, table 9.2. And what is the decibel range for normal conversation? So normal conversation is within this range, and it's 40 decibels to 50 decibels. And then what is the threshold for pain from sound? So that's going to be 120 decibels or more. And then it's going to start to hurt your ears and tell you, okay, maybe you better cover your ears. So as you can see, in example 9.4, the rifle was 140 decibels. So that's why we wear ear protection when we go shooting, right? Okay, we're going to do it, and I want you to pause the video after I read it and try to figure it out yourself, and then keep playing the video. The sound from a typical vacuum cleaner is about 60 decibels, while the sound from a rifle firing is about 140 decibels. How many times larger is the intensity of the waves coming from the rifle as compared to those coming from the vacuum cleaner? Remember that in the bell scale, every increase of 10 decibels is the same as a 10-fold increase in the intensity of the sound wave. So you need to find the difference in the sound intensity first. That's subtraction, by the way. And then find the 10-fold increase. Okay, so this is where you would pause the video and try to figure that out, but I'm going to keep going. So you have 140 decibels minus 60 decibels. That equals 80 decibels. And that's the difference. Okay? So the rifle is 80 decibels louder. And then each 10 decibels equals a 10-fold increase in the sound wave intensity. So that means if it's 80 decibels louder, it's going to be 10 times 10 times 10 times 10, that's 4, times 10 times 10 times 10 times 10, that's 1, 2, 3, 4, 5, 6, 7, 8. Okay? and that means it's 100 million times larger in intensity if you put that in your calculator and calculate that out. So that's your answer. Moving on to pitch. Frequency of the sound, it determines how high or low a sound is. So if you think of the notes in music, not the loudness. When I say high or low, I mean more like notes in music. And just remember that pitch is frequency and loudness is the amplitude of the wave. So sound is a longitudinal wave. It doesn't look like a transverse wave, but just to show you really quickly, the longer wavelength is going to have a lower frequency. You're going to have the waves coming at a lower frequency less often, as opposed to if you have a shorter wavelength, you're going to have a higher frequency. You're going to see more waves because they're closer together. Okay, so this is the wavelength, not the amplitude. Right now we're talking about. So the wavelength of the wave was determined by how far the air could travel up and down the bottle. The long wavelength was when it could travel all the way to the bottom. There's more distance for the air to travel, basically. So showing you the equation, velocity equals wavelength times frequency. When the wavelength increases, the frequency has to decrease. They're inversely proportional to still have the same velocity. And then the opposite is true too. Let's say the wavelength decreases, the frequency has to decrease to have the same velocity. This is a good thing to put in your notes too, so you remember that. And then remember that frequency equals hertz. It's measured in cycles per second. So that's like how many cycles per 1 second. Sorry, that says second. And the human ear detects frequencies in the air of 20 hertz to 20,000 hertz. We're not talking about decibels. It's hertz now, so 20 hertz to 20,000 hertz. The Doppler effect is a change in sound frequency caused by the motion of the source, motion of the listener, or both. Okay, so the object is a car. It's moving this direction, and the sound waves are getting bunched up in the front of it, kind of like what we talked about with the sonic boom. Okay, so if you think about the wavelength here, the wavelength for this person is going to be greater than the wavelength for what this person's hearing. So the person under that B I wrote, here's a higher pitch because the sound waves bunch together and they have a higher frequency. When the ambulance passes, the observer A hears a lower pitch. So this guy's hearing a higher pitch. This guy's hearing a lower pitch. Let's say this keeps on driving past. Eventually, he's going to experience that lower pitch that observer A was hearing. And you can do an experiment yourself and your parent with honking a car horn. So if you have like a long stretch of road, you can go out and do this where you stand still and you have the person honk the horn and hold it down as they're driving past you, and kind of observe what it sounds like when they're getting closer to you, and then when they're right in front of you, and then as they pass you. The next part of your book talks about the uses for sound waves, and I just wanted to go over the frequency range for sound waves so that you kind of understand. So there's infrasonic, which is so quiet that we can't hear it. There's audible, which is what we can hear with our human ears. And then there's ultrasonic. And so the frequency of the wave changes. So with infrasonic, you're going to have a lower frequency wave. And remember, the frequency is from peak to peak, okay? Then it's going to get a little bit higher frequency. And then the ultrasonic is so high, we can't hear it. Audible sound for us is 20 hertz to 20,000 hertz. Okay, so anything greater than 20,000 hertz is ultrasonic. This is like 200 million hertz. It can go up to. And then infrasonic is just anything less than 20 hertz that we can't hear. So these sound waves can be used in different ways to create images. We can use sound waves to kind of see things by calculating the distance it takes the sound wave to bounce off an object and return back to the sender. So let's say we have an object here and the sender sends out a sound wave. It bounces off. Some of that is absorbed into the object. Okay, so some of it continues and then some of it bounces back. I'm trying to do this in a dotted line. Okay, and so they can measure the distance it took, and they can create images with machines that calculate that. And also, different types of objects absorb sound waves in different ways. Like, you can see this room that I'm in. I'll show you. I'm in the library in one of the study rooms. And do you see what the walls are made of? This is to absorb sound so that the sound isn't bouncing off, but a lot of it is being absorbed. Okay, so this would be something that the sound would bounce off of, like if you have a hardwood floor, bounces off a hardwood floor a lot more than if you put a rug on the floor, right? The sound waves are absorbed more by the rug, and so you won't hear as much of an echo. So in your book, it has the ultrasonic ruler. The ultrasonic ruler emits a short sound, then it calculates the distance the sound wave traveled based on how long it took to bounce off and return, and then measures the speed of sound using a temperature reading, because remember, the temperature matters when you're measuring the speed of sound. The ultrasonic sound waves are used in the same way for medical imaging, which is seeing inside the body, such as visualizing a baby inside a pregnant mother. It creates like a 3D map of what the baby looks like. This method is also used in sonar, which uses ultrasonic waves to map out the bottom of the ocean or show you the depth. If you're boating and you want to know where the fish are, where to drop a line to go fishing, you want to know where the school of fish is, and you can use sonar to locate the fish. Also, submarines use it to track other ships. Bats use sonar to kind of see at night to catch insects in flight with amazing precision. The bats use the amplitude of the reflected waves to understand what the object is made of, so they can tell the difference between a leaf or a pebble or a bug, and they send out varying frequencies and can analyze the amplitude of the reflected waves at different frequencies. And they do this extremely quickly while flying in the dark at high speeds. So there is this video that I have that is so awesome. It's a Moody Bible Institute study done, and they taped the bat's eyes shut, and they had it fly through bars that only were big enough for it to barely fit through. So there were bars in this room, and the bat's wingspan was like just enough to be able to fit between the bars. Okay, so the first study, they covered up its eyes, and they released it and let it fly, and it flew through the bars totally fine. Okay, the next study, they actually taped its mouth shut. Okay, and then they let it go and saw what it did, and it banged in here and banged in here, and it finally gave up and laid down. And it couldn't fly because it couldn't send out those, I believe it's high frequencies that they're sending out to bounce off objects so that they can see, because they're not actually using, they do have good eyesight, but they're not using their eyes so much when they're flying as the sounds, the sonar. So that's the end of Module 9 on sound waves. Your next step is you're going to make sure your notes are organized, and you'll have all your notes on Module 9 for the test and for your brain. You're going to finish all the on your own questions, and then your next step will be to do the study questions. You're going to do the questions and check your answers. There's no point in doing the questions if you're not going to check your answers, because if you do it incorrectly, you're learning the incorrect way. So make sure you check your answers. And then just like go through your notes and organize them. I have things like this in my notes, like the picture I drew for you. I'm a very visual person, and so I'm going to do notes a lot in pictures. It makes it easier for me to find the information. Or I put as much as I could on one page to just kind of remind myself, and you're welcome to pause the video and copy this if you want. I'm totally fine with that. And just have it all in one spot, because when you go to take the test, remember one of the things you have to do is choose an equation. So if you have all the equations in one spot, it's going to help you. All right. Thanks for watching.